All right. So, to clarify a couple things, let's get started. This is our last content lecture in Engineering 213. And what I mean by that is this is the last new, fresh topic we are going to cover this semester. When we come back from break, it will be review of what we've already done, not anything new, okay? So this is it, okay? All right? With that, I am giving you a homework today. It is due on Friday. I am not having it due after break. I want it due before you go on break, so that you don't have to worry about this class over break. I want it to be turkey time or tofu time or whatever your dietary choices are. I'm a vegetarian, so I get it. But whatever makes sense for you. But I want this class to be not a big deal. We do not have class on Friday. This is it. And I think that we will end a little bit early today. So, because I know that there is a celebration coming up in chemistry. Yep. That you all are just going to have to sulfur through.
All the way to the business building.
Have to sulfur through.
I thought it was fine.
Thank you. I was trying to get a good reaction. Chemical reaction. My jokes are pretty basic when it comes to chemistry.
Oh my God.
My jokes are so basic you could stick them in acid to balance the pH. Okay. Did everybody get the code? I'm such a dork. I know. It's okay. All right, everybody. Okay, so let's talk about friction. Today what we're going to do is we're basically going to incorporate trig into our problems today, because basically what I'm going to do is take a friction problem, take a block, put it on an incline, and say, is the block going to slide down the ramp or not? And while we have some trig, we also have a little bit of graphing and algebra showing up here in a bit. But let's just sort of recall where we left off. So last time, what we were really trying to do is explore the effect of friction on motion or potential motion in engineering mechanics. And a lot of it's centered around the two parameters that you see here, an F sub m and an F sub k, which is basically taking coefficients of friction and multiplying them by their normal force. Now, what is the normal force? The normal force is a reaction from a plane on an object in question, okay? So, for example, if we're looking at, let's say, this box, this would be a somewhat complicated situation. I don't want to say complicated, but you'd have to do a little bit of work on this. So if we're talking about this, this situation, the block has a weight W. That weight acts in the direction of gravity. It acts downward regardless of the inclination of the ramp. What we've got to do is break that normal component up into what I'll call X and Y. And by X and Y, I mean, X and Y. And so you could think of normal and tangential if you would like those terms. And so not only would we have to break the W into an X and Y, but we would have to break the applied load into an X and Y. And so the normal force would be the force required in this direction to attain equilibrium. Okay? Now, when it comes to the coefficients of friction, I don't expect you to just sort of know them. Okay? When it comes to a coefficient of friction in a course like this, you're either going to be given those coefficients of friction, or you might have a problem where you have to figure out what it needs to be to satisfy certain situations. Like for example, if you had like a a block with a force on it, and you might say, okay, what does the coefficient of friction need to be such that it won't move? So you have to solve for mu sub s or whatnot. But it's not going to be something that you just have to assume or guess. One thing that you do want to keep in mind, though, is that the coefficient of kinetic friction is lower than the coefficient of static friction, and if you want a rough idea, about 75%, something about like that. Okay, sound good? All right, so no Yoshi today, I know, but we're just going to have a block today. But again, a lot I have here on this slide is in regard to the normal force, which I talked about on the last slide. But again, if you want to think of what the normal force is, think of the normal force as sort of the plane's reaction to the applied loads. So if you've got a bunch of loads being applied to the plane, then N is the reaction required to keep the box in equilibrium from a direction like this, from a direction that way. Now, the one thing that we're going to have to be careful of is a little bit of trig, and more specifically what happens with perpendicular lines. So I'm going to break it back to basic algebra. So if I give you the equation of a line and I say y equals mx plus b, and then I ask you, okay, what is the slope of a line perpendicular to the line I gave you? The slope would be the negative reciprocal. Do you all remember that? So if you have a line that has a slope of 2/3, the line perpendicular to that has a slope of 3/2 or negative 3/2. Okay? Does everybody remember that from algebra? Okay. So how does that apply to like this? Okay. So the idea is, and I'm gonna draw one here on the slide that's maybe a little goofy in its proportions, but I think it does kind of make the point. So let's say that I have a box on a ramp, and let's give it some like really, really light slope ratio. I got one. Let's do like 1 to 12. Okay, that's not a goofy slope ratio. That's actually a really practical slope ratio, because 1 in 12 is the maximum slope ratio that you can have to be ADA compliant. So ramps and whatnot, handicap ramps. So what's going to happen is I'm going to have some weight that's acting downward, right? Okay. So by the way, what is 1 to 12? 112. So the hypotenuse is going to be something like 145. Is that right? Square root of 145. Okay. So what I'm going to do is I'm going to take the force that's on this plane, and I'm going to split it up into an x and y component. And the x or the y component is going to be a lot bigger than the x component, right? I mean, think about it like this. If the ramp was perfectly flat, all the force would go down, right? So what I'm saying is I'm picking the ramp up on the side just a little bit, okay? And if I pick the ramp up just a little bit, some of that weight is going to want to push the block down the ramp, right? Does that make sense? What I'm saying is that this force is going to be weight times this, and this force is going to be weight times that, okay? That the smaller component is going to be going like this. And so what I have here at the bottom is sort of a formalization of that if I have a block where this is a 5 to 12, so the numbers are a little bit bigger, 5 to 12, 5, 12, and that makes that 13. Then when I split this up into x and y, this is the 12 and that's the 5. So the way you can sort of look at it is the 12 is associated with the horizontal, the 5 is associated with the vertical, but then when you go here, you flip it. The 5 is associated with the horizontal, 12 is associated with the vertical, because it's perpendicular, right? You're flipping the slope ratios, just like here, you're flipping the fraction. It's the same idea. Does that make sense? And don't worry, we're going to have a full-blown example to sort of make the point. So, sound good? Okay. So let's do our example, okay? Oh, let's pull this up in the notebook. Okay. So I have here a block that's at a 3, 4, 5. So I like the 3, 4, 5 just because the trig makes that pretty easy. Okay. And the 3, 4, 5. Again, we can do a lot of the math sort of in our head. The block is 300 pounds. Now, think about what's happening. Without the 100 pounds, the block is wanting to slide down the ramp. So the 100 pounds is sort of helping prevent that from happening. And what we want to know is the crate in equilibrium? And I guess the question is, that's a loaded question because there could be 3 possibilities, right? The crate could be in equilibrium, the crate could be sliding down the ramp, or the crate could be sliding up the ramp. You know what I mean? If we have a ramp that's covered in Crisco, and we're pushing it upwards with 100 pounds, that might be enough to slide it up the ramp too. That's very possible, right? So there's a couple different options of what could happen. We just sort of need to reason our way through it, okay? So I do have a couple notes here in terms of points to consider. So the 300-pound load acts as a weight. Okay, whenever you have a weight, it's down. Okay, the ramp or the inclination of the ramp doesn't affect how weight acts. Weight acts downward. Okay, we're going to need to split this into X and Y components, but again, we're going to need to be careful about our approach. And when we're done with the question, I want to think about these sort of brain teasers at the end, but let's see what we can figure out. Okay. All right. Now, this is a 3, 4, 5 triangle, okay? So let's do a couple things off the top of our head. So let's see. So okay, weight components. All right. So the first thing I'm going to do is I'm going to take the 300 pounds and I'm going to do this. Now, why am I doing that? Well, I'm doing that because, what are 3/5 and 4/5? If I'm thinking about this triangle, what would the 3/5 and 4/5 be? Components, but what, boom, that's what I'm talking about. They're the sine and cosine of that triangle. So if I take 300 times the sine or 300 times the cosine, what I'm essentially doing is taking that weight and I'm splitting it up into X and Y components. And when I say X and Y components, what I'm talking about is I'm sort of treating the system like this, okay? I'm saying, okay, let's not deal with X and Y like this. Let's deal with it along the ramp, okay? So I hope you'll permit me to just tell you that's 180 and that's 240. Okay. All right, sound good? Now let's do a free body diagram. Okay. All right, so let's put our ramp here. Okay, and let's recognize that, again, that was a 3, 4. Okay, and I'm going to put sort of a shadow of where the box was. Okay. Now, what I'm going to do is I'm going to split this up, right here at the box. So the centroid of the box is about right there. What I'm going to do is I'm going to say this is going to be a force and that's going to be a force. And I guess my question for from the brain teasing perspective is this force right here, which we'll say is the vertical component. because we're defining our coordinate system to sort of be like this. So I guess this component right here, that force, is that 240 or is that 180? 240. That's 100% right. $180. And so the way I'm reasoning through that is this, okay? Up here, see how the horizontal component is bigger? Like this is 3, this is 4, so the horizontal component is bigger. But perpendicularly, the vertical component is bigger. That's how I'm reasoning through that. Does that make sense? Because, I mean, I have the ramp up, but I don't have it up like past 45 degrees. It's more flat than it is up like this. So that vertical part's going to be a little bigger. Okay. All right. I also have to account for the fact that that's 100 pounds. Okay. All right. Let me scooch this down a little bit. Okay, let's scooch this down. All right. So the first thing I want to do is, and a good strategy on a friction problem is to try and figure out what the normal force is. Okay? So I'm going to sum forces in the y direction. You're going to laugh maybe a little bit at this, but I'm going to sort of draw it like that. Because y in this case isn't like up. Y is this way. Okay? So if I do that, I'm going to have a positive n minus 240 pounds and I get that. Okay. All right. So far, so good? Okay, now, I think what we ought to do, given this scenario, is let's suppose box is sliding down the ramp. Okay. If the box is sliding down the ramp, in what direction is the friction force acting? Up the ramp. So okay. Or maybe I'll tell you what. I might rewrite this a bit. Instead of sliding, we'll say tending to slide. Let's say tending to slide down the ramp. Sorry. And I'll say tending to slide down the ramp because I am going to sum forces in the x direction and set them equal to 0. Okay. So if it's tending to slide down the ramp, but it's still static. Okay. So now what we're going to do is we're going to sum forces in the x direction, and x sort of goes like that. So what do we have? Let's see. We've got FF positive 100 pounds minus 180 pounds is 0. Is that fair how I wrote that? Because the friction's going up, the 100 pounds is going up the ramp, and the 180 pounds is going down the ramp. Okay? Does that make sense? Okay, so therefore, F sub F has got to equal 80 pounds. Okay, with me so far? All right, before I start doing any more calcs, everybody okay with this? Okay. So what does this 80 pounds mean? Let's just sort of wrap our heads around this. What this is saying is that the box is on the ramp. We're supposing that the box is sitting still. It's not moving, okay? So for that box to sit still, I better have a frictional force generated of 80 pounds, okay? How about this? Let's write it like this. Okay. What is FM? It's going to be mu sub s times n. Mu sub s was 0.25. What was n?
Would it be 60?
What?
Would it be 60?
Oh, after I calculate it, yeah. This is 240. You're saying the answer's 60.
Yes.
Yes. I thought you were saying this was 60. I was like, I thought you were saying that was 60. I was like, what? Yeah, no, 60 pounds. Okay. So, can somebody tell me, like, what, where do you take all this? What's happening here? So, in order to keep this box in equilibrium, I'm saying that the frictional force needs to be 80 pounds. Can I get 80 pounds? Remember, what does the friction graph sort of look like, right? The friction graph looks like this, right? Here's the graph. We can generate friction up until Fm. Then we start moving and we get Fk. So I'm saying to keep the box in equilibrium, we need 80 pounds of friction. Is the box in equilibrium? Is the box sitting still? No. The box is moving, okay? That's my answer to the question. So the question is the box in equilibrium? No. So we'll say that since FF is greater than FM, box is sliding down. Okay. By the way, if box is in motion, what is F sub F? Like, this is impossible, right? Is basically what this is saying. This is impossible. We can't generate 80 pounds. So if the box is in motion, how much friction can we generate? We can generate the kinetic friction, right? Under motion, which is and that's going to be 48 pounds. Does that make sense? Okay. So I want to guess.
Where'd the 480 pounds?
Oh, that's supposed to be 240. I was getting ahead of myself. You're right. That's 240. Thank you. That was a whoopsie because I was getting ahead of myself. All right. I want to give you two things to consider. I'm not going to do these problems for you, but I just want you to think about sort of tying it to our Yoshi example. Note, so what would the 100-pound force need to be to prevent motion? That one's actually pretty easy, isn't it? Can anybody tell me what that would be? 120. Now, how are you getting 120? Well, if we go back to, this right here, okay? In order to keep the box in equilibrium, friction needs to generate 80 pounds, right? But I can only get 60 before motion occurs. So I need another 20 pounds to keep the box where it is, right? I don't have enough. But now, and this is just something to ponder, now how much force would I need to push the box up the ramp? I'm not going to do that one for you. I want you to think about it. Here's another one. Consider let's leave the 100 pounds as is. Don't change the 100 pounds. What would theta need to be to prevent motion? Okay? And you're probably not, or maybe you're not following what I'm talking about, but like, for example, we said that Wx was, how do we want to put this? We'll say W times 4/5 and Wy was W times 3/5. I mean, that's basically kind of what we were doing, right? Why don't we instead reformulate the problem and say, what about Wx is W times the cosine of theta, and make that times the sine of theta. And then now redo the problem, but treat theta as a variable and ask, okay, at what angle will it not slide? So, for example, what's the inverse tangent of 3/4? Somebody give me that, like, say, to 2 decimal places. You'd think I remember that, but I make it a point to not deal with the angle because I just deal with the 3 and the 4, so I sort of forget that. So what I'm saying with this problem is that at 36.87 degrees, the box slides down the hill. So what if I started changing the angle? At what point would the box not slide? You see what I mean? So just something to think about. It's not really that difficult, but it's sort of one of those pause and ponder type problems. Okay. Does anybody have any questions? It's just something to think about. Okay. I'm going to give you a homework, which is going to activate today. It's going to close Friday at 11. What are we going to do in class on Friday? Nothing, because we're not going to have class on Friday. When we come back on Monday, so just to make sure everybody's clear, when we come back on Monday, Wednesday, Friday, we review for the test, the final. And I do have one homework assignment over next week, but it's just doing the course eval and a bonus assignment for that. That's all I have, everybody. You all have yourself a wonderful Thanksgiving break. We will see you all when you get back.